this talk, I'm going to present you our effort to develop a climatology of extreme rainfall in Switzerland based on 12 years of radio-derived data. And the objective is, of course, exploit the high spatial resolution of the weather radar to learn more about the precipitation regime in the Alps, and mainly to provide simple statistical analysis needed for climate model validations. Because from the literature, it seems that the largest increases in extreme rainfall intensity are likely to occur in sub-daily storms, but actually for many parts of the world, including the Alps, are missing some high-resolution observational references with which to compare the models. Just an example from a recent paper in which they show the projection of summer precipitation on hourly time scale, so the differences between a scenario in future and a control scenario in a recent past. And you can see that, like here, for different models, 3 different models and different percentiles of rainfall, the models produce these patterns which needs to be at least validated with high-resolution data in order to build confidence on the projected changes. We also want to compare gauge and combi-precip extreme precipitation, so to see the point scale versus volume integral scale problem in the context of the extremes, and also a final goal, provide return levels of rainfall over different spatial and temporal aggregations. So the data set I'm using is combi-precip. A lot has already been told about this product, which merged the rain gauge and radar data. And we use 12 years of data. You can see we are using 2 different radar generations. And then I use 68 rain gauges, which is the number of rain gauges which is available since 2005. And I use this rain gauge to compare the corresponding pixel of combi-precip. As I was telling before, and all the radar were changed in the recent past, so this is already an issue to build a climatology. 12 years of data, so this is very shorter than the typical period taken for climatology of 30 years. And also, of course, we have the issue with homogeneity of the data. We have 2 radar generations and 2 new radars in the last year, from 2014 and from 2016. So an effort we did to try to homogenize the data was to compute residual global bias of combi-precip with the rain gauge. It means that we just computed the total rainfall at every hour of the archive from the rain gauges and from corresponding combi-precip pixel above. And we try to compute this bias and to use it to correct the data. So we simply apply this as a multiplicative correction factor to the data. You can see that the bias is in generally low. So in percentage, it's just most of the time lower than 12%. And this was our first effort in order to create an homogenized data set. Of course, we know that it's not kind of a typical homogenized data set like normally we find in climatology. So I'm going to show you some results about the agreement between the rain gauge values and the radar-derived extreme precipitation. And then the method was the common leave one out scheme. So in order to perform an independent verification of rain gauge and combi-precip, the rain gauge measurements are compared with the corresponding independent combi-precip values obtained without considering the rain gauge at the same and previous time instant. In this way, we can have an idea of the error we are observing when looking at extremes. To do that, I just created an easy contingency table, taking as a threshold here the 99.5 percentile, which for our data set corresponds in general to the 10 most intense samples per year. And I computed some simple score, like the bias of the hits. So every time an extreme is an extreme for rain gauge, both rain gauge and combi-precip, I just compute basically the difference between the two, probability of detection and false alarm ratio. And looking at the results, now you have a box plot which describes the distribution of these scores for the 68 rain gauges and overlying combi-precip pixels, and for the different seasons and for 3 different accumulations, 1 hour, 6 hours, and 24 hours. So in the top, you can see the bias of fits. So this is the typical error once an hour is an extreme for both rain gauge and combi-precip. And in general, the median value of this is between minus 2.5 to minus 7%. It means that for that hours which are extremes or which fall in the tail of both the instruments, we are generally underestimating the values of the extremes. Then probability of detection, the median value is between 0.5 to 0.65. And it means that 50 to 65% of the rain gauges are extremes also according to combi-precip. Looking at the false alarm ratio, which is the fraction of combi-precip extreme, which are not actually extremes according to the rain gauges, the median values at least is comprised between 0.4 to 0.5. And you can see that also the scores tend to be better for larger accumulations, so for 24-hour rainfall. And there is a slight signal that in winter, at least POD and FAR are a bit lower than in the other seasons. I also looked at the spatial distribution of these bias of fits. Here it's for 1 hour rainfall and for the different seasons. And basically you can see sorry, that it's difficult to find a geographical pattern. We were expecting also to see larger errors in the region in which the radar has a lower visibility, but this was not actually the case. And this sort also tells us that even though the visibility of the radar was not constant, constant also throughout these 12 years of our period, the error are not too much affected by this fact. Then I concentrated on 1 hour rainfall, and I let the threshold for the contingency table vary between the 90 and to the 99.9 percentile and computing the same scores. And I plot here the 3 scores. So from the 90 percentile, which in our data set correspond to 2,300 hours, to the 99.9, which correspond to the most intense 25 hours. So we are really trying to see how combi-precip performs in the case of extreme rainfall. And you can see that, of course, the scores tend to decrease or to get worse by increasing the percentiles. Sorry. And for example, the POD range from 0.8 to around 0.5, and the false alarm from 0.3 to the 0.4. So from here, I think it's useful to, once you know the kind of events you are looking at, you can have an idea of the error or of the difference between the two instruments, because of course we are not expecting to have exactly the same value, so 0 errors since we are looking at the point measurements and then a volume integral measurement. So here we are not taking into account, or better, the subpixel rainfall variability is reflected in these results, the radar error is reflected in these results. So we know that there is an error, but yeah, by looking at this kind of graph, we can kind of quantify all the results of all the different sources of errors. Okay, now some maps. I show you the spatial distribution of extremes, and here I go back to the definition, the 99.5 percentile, so basically the 10 most intense samples per year. This is a spatial distribution of these values, and you can see that there are, of course, seasonal variations. The largest values are observed in summer in the southern part of Switzerland, but also along the first slopes of the Alps, north of the Alps, and on the Jura mountains, we tend to have large values. And going to the 24 hours rainfall extremes, the pattern is a bit different. You can see that now the extremes tend to accumulate on the southern part of the Alps in autumn, originating the typical bands of heavy precipitation we observe in Switzerland. In these maps, you can see that there are still some radar-related features. For example, we can see some azimuths which are masked by obstacles, basically, in proximity of the radar site. And also some other regions in which we don't see quite well. Luckily, most of them are out of Switzerland, but for example, I masked all the regions which have a frequency of observing rainfall very different from the rest of the spatial domain. So the message is that I think you can use this data to build also climatology, but it's not like that if someone asks you the data, you just give the data to a customer and without explaining this kind of problems related to the radar scan strategy. And depending on the place in which you are interested, you can really to be confident of the quality of your radar or not. So in summary, I think we can start looking at extreme, even though it's not 100% homogeneous data set. I show you our effort to try to make the data set homogeneous, but of course it is not, and I hope in 2027 here to give you a climatology which is 100% homogeneous based on their new generation of radar. Also, it was interesting to see a known feature of subdaily alpine precipitation extremes. And I didn't have time, of course, today to show you, but in the paper here you can find all the other interesting maps, for example, related to the temporal clustering of extreme, to the seasonality, etc. Then the agreement between the radar-derived and rain-gauge rainfall increases with diminishing the severity of the threshold used to define extreme, as we have seen before, and with increasing the length of the accumulation period, as we were expecting. And then we have seen extremes tends to be lower for combi-precip than for rain gauge, till 7% lower. Half or 50% to 65% of rain gauge extremes are extremes, also according to combi-precip. And 40 to 50% of combi-precip extreme are not extreme for the rain gauges. As an outlook for future work, we would like to try modeling of precipitation. I did some trial using the general Pareto distribution. Since we only 12 years of data, we cannot use GEV. I'm still working on that. Here is just an example of a 2-season return level for 1 hour rainfall. And the first image shows that the pattern can be quite scattered, and there are, as in all the maps I show you before, strong gradients of rainfall which are due to the orography. So this also said that here in the Alps it's quite difficult to apply some regional frequency analysis approach because of the strong variations of heavy rainfall. And this is basically objective number 4 that I showed at the beginning. That's it. Thank you for your attention.
At some point you said that the map of the device didn't show patterns, interesting patterns, but I could see some interesting features. Okay.
You can see scientists, just to mention one.
I was
stay.
You said that you have something like more or less 7% underestimation of the extremes by combi precipitation compared to rain gauges. Do you have an explanation for that?
Yes, one issue could be related to the fact that that extremes are usually produced by convective events for which combi precip has still some problems. As was already mentioned, we have every time you have a convective cell which is between the rain gauge, the combi precip for combi precip it's difficult to reproduce it because you actually don't have any rain gauge at that place of the convective cell. So what we see is that you have an underestimation of convection. This could be one. I think it's the main one, yes.
And you should not forget that up to 2011, the combi precip was using only 70 gauges, 68. The number of gauges is increasing only after those years. And in this sense, when Luca will present again this climatology using 260 gauges and 5 radar in 2024, it's going to be much better.
Welcome.
Yeah, no shirt.
Yes, I'm not having the transmission yet. I'll wait until it's blue so I don't get a strange thing. As we are waiting here, let me just remind those people who have walked in and who are from outside of the hotel, if you are staying for the workshop dinner, please, as you're going for coffee break, write down your name on the board outside to make sure you get a meal.
Okay. Hello everyone. So I changed a bit my title compared to the program.